guys, so we'll do a tutorial today based on the topics what we have learned. So last two lectures, basically lecture 26 and 27. So we are doing a couple of tutorials, like, because these things we will understand it more better using more and more problem solving. So that's the reason why I'm giving so many tutorials. So now first we will start with the objective type question, which basically will help us making a quick recap of whatever we have studied. So first is, if we decrease the confidence coefficient for a fixed n, okay, we have decreased the confidence coefficient. We have decreased the confidence coefficient, meaning what? Means we have increased alpha, right? We have decreased the confidence coefficient, that means we have increased alpha. We have decreased 1 minus alpha, it is 1 minus alpha is decreasing, means we have increased alpha. If we decrease the confidence coefficient for a fixed n, we decrease the weight of the confidence interval. What is the weight of the confidence interval? It's basically the error of estimation. Remember, my mu square value will lie between what range? X bar plus minus, what was that? Remember? Z alpha by 2 Z alpha by 2 sigma by root n. So my mu square will lie within this range. My mu, not mu square. My mu will lie within this range. Similarly, if we talk of variance, proportion, whatever it is, accordingly this value will get changed. So this is my total range. Okay. So this is my total weight. My weight is basically E. What is this? This value is E. So I can write E is equals to Z of alpha by 2 sigma by root n. So here when I am increasing alpha, you see the diagram here from the table. Increasing alpha means what? I am increasing the critical region. Increase it. Suppose if my alpha was here, basically here, means say 0.1, now I am increasing to 0.5. I am increasing this area. Alpha I am increasing means from here I am bringing to here. Before it was this portion. Now increasing means I added this portion as well. So when I am increasing alpha, what is happening? My Z value is decreasing because this is 0. From 0, I am going this way, it is increasing. Z value is increasing. When I am increasing alpha, my Z value is decreasing. So in this expression, when my Z value is decreasing, what is happening? Z value is decreasing means my E will be smaller. My error of estimation will be smaller. When my error of estimation will be smaller, that means my weight will become less, isn't it? So we decrease the weight of the confidence interval. That is true. Okay. So next question, if a 95% confidence interval on mu was from 50.5 to 60.6, this is the confidence interval given. We would reject the null hypothesis that mu is equals to 60 at 0.05 level of significance. So this is my confidence interval. So mu very well lies within this region, because this range is 50.5 to 60.6. 60 lies in this region. So any value that lie in this region, we will not reject the null hypothesis, isn't it? That's what we have seen. If the value lies within the confidence interval, then the null hypothesis is not rejected. So this value is lying within this region, so we will not reject. So this is false. So if the sample size is increased and the confidence coefficient remains constant, the weight of the confidence interval will decrease. Again, same. E, what is my E? E is equals to Z alpha by 2 sigma by root n. Root n is in the denominator. If denominator is bigger, what happens? Our value becomes smaller. So what happens? If the sample size is increased, if I increase the sample size, my E will decrease. E means the weight will decrease. Then, and the confidence coefficient remains constant, means alpha remains same, but I am increasing the sample size. The weight of the confidence interval will decrease. Yeah, the weight will decrease. That is one of the advantages. If I increase the sample size, then what happens? My precision is also increasing. At the same time, I am not losing on the confidence also. Usually what happens when I change the confidence coefficient means when I reduce the confidence coefficient, my precision is increasing, but my confidence is going down, isn't it? But if I increase the sample size, still my precision is increased, but my confidence does not change. My confidence still remains the same. So that is the advantage of having a bigger sample size. So this is true. The variance of a binomial proportion is NPQ or NP1 minus P. Is it true? Just now we have seen it. I mean, sorry, not just now. In the last lecture. In the last lecture we have seen. So the variance of a binomial proportion is P into 1 minus P. P into Q. That is the variance of a binomial proportion. So this is false. Again, there are some more questions. The sampling distribution of a proportion is approximated by chi-square distribution. Is it true? We have seen it in the last lecture. The sampling distribution of a proportion is not approximated by chi-square distribution, it is approximated by the normal distribution. Considering this as a binomial population and considering a bigger sample size, it is approximated by normal distribution. It is not chi-square distribution. The t-test can be applied with absolutely no assumption about the distribution of the population. Completely false. T-test is very much sensitivity to normality assumption of the population. The degree of freedom for a t-test do not necessarily depend on the sample size used in computing the mean. Okay, this thing. I did not take this in the class, so we will explain it here. Usually what happens, whatever we have seen in the t-test or chi-square, it has one parameter, that is the degrees of freedom. And degrees of freedom, how do we take? It is the sample size, isn't it? Sample size minus 1 is our degrees of freedom. For t-test, chi-square test, f-square test, or f-test, for all these tests we have seen, they have just one parameter. That parameter is the degrees of freedom. What is the degrees of freedom? Degrees of freedom is the sample size minus 1. But this question... But you see, there are some situation, like let me take an example. Suppose I'm interested, suppose a factory is producing stone chips, you know, this small stone chips. So a factory is producing that, and I want to know the mean weight of these stone chips. So a factory is producing huge number of stone chips, and I'm interested in a mean of these stone chips, because I need a particular size of stone chips for building something, I want to build something, okay, some house or some whatever, some hotel, whatever it is. So now, how do I for that, definitely I should, to know the mean of the population, I'll have to take a sample. So suppose taking a small sample will definitely make no sense in such cases. We'll take a bigger sample. Suppose we took a sample of say around 100 stones. Definitely we will not count 1, 2, on an estimate we have taken around 100 stones, and now we'll have to take the mean of these 100 stones. How we'll have to take the mean of each and every stones? We'll have to weigh it, what is the weight, and then we'll have to find out the mean. No, that we won't do that. We are not so jobless. So what we will do is that we will take this whole 100 samples in a weighing machine. We will just weigh the weight of these 100 stones and divide it by 100. That becomes my mean weight of the stones. Okay, that is my mean weight of the stones. Now what is the variance of this stone? So variance, definitely I cannot just weigh it together and can find out the variance, and it is also not possible for me to find out the variance of these 100 stones. My sample size I have taken 100, so it is not possible for me to find the variance of this 100 stone also. From each stone I will subtract from weight of each stone, I will subtract it from the mean, whatever mean I got. That is also not a very interesting job, right? So what I'll do, I'll take, suppose I took 10 stones, and for these 10 stones I've sincerely calculated the variance. For each stone, variance, you know how to calculate. I'll have to calculate from the mean. I'll subtract this value weight of each stones. So I have taken from this sample, I have taken a subsample of say 10, and from there I found out the variance. So in this case, my degrees of freedom will not be 100 minus 1, 99. Later my degrees of freedom will be 10 minus 1, 9. Okay, so that is very much correct. And in this sort of situations where it is really not feasible to find out the variance of the whole sample, this sort of thing, this process is also taken up. So the degrees of freedom for t-test do not necessarily see the word, depend on the sample size used in computing the mean. Yes, it is very true. It depends on the sample size used for computing the variance. So this statement is true. Now we'll see some problems. So last two lectures, what we have learned, we tried to find out confidence interval, basically confidence interval, and how it changes with the sample size, what is the error of estimation, and all those things we have learned, right? And how to infer about the population, how to infer about the variance, population proportion, how to infer about the variance of the population. We have learned in the last two lectures, we have learned all those. So based on that, we will be seeing some problems. The first question you see, the average zinc concentration recovered from a sample measurement taken in 36 different locations in a river. So 36 different locations, that means my N is 36. In a river is found to be 2.6 grams per milliliter. So average, that means my is this mu or x bar? This is x bar, because this is, we are talking about the sample, right? So my, what is my x bar? X bar is 2.6. Find a 95% confidence interval for the mean zinc concentration in the river. Okay, we have to find out a confidence interval. Assume that the population standard deviation is 0.3. Okay, good. That is, they have given the population standard deviation. They have assumed that population standard deviation is 0.3, and we have to find out the confidence interval. We can very well find out the confidence interval because we will be using Z alpha by 2 instead of T alpha by 2, right? So this is given significance level. So this is how we calculate the confidence interval, isn't it? Confidence interval, how we calculate? X bar minus Z alpha by 2 sigma by root n. This is less than equals to mu. This is less than equals to x bar plus Z alpha by 2 what to say, sigma by root n, isn't it? So that's all. We have all the value. What is the 5% means 0.025. 0.025 corresponding to 0.025, from the Z table we will find out value is 1.96. You can check it. That is 1.96. This is x bar value. This is the variance sigma, and we have taken from 36 different locations. So root n is 36. Okay. So this is the confidence interval. Fine. Similar type of question. Suppose that a population mean is to be estimated from a sample size of 25 from a normal population with sigma is equals to 5.0. And previous problem also, this problem also, population mean is not, we don't have any hypothesized value. So we just have to estimate from the sample value. Find a maximum error of estimation with confidence coefficient 0.95. So here we have to find out the maximum error of estimation. Basically, we have to find out the width. What changes if n is increased to 100 while the confidence coefficient remains 0.95? We have already seen when we increase the n, what happens? Our width decreases, isn't it? When we increase the n, our width decreases. When we decrease our confidence coefficient, our width decreases. When we increase our significance level, our width decreases. We have seen that. So this is the formula for E. What is E? E is nothing but Z alpha by 2 into sigma by root n. So this is Z alpha by 2. It is 0.95 is the significance coefficient. That means 5% is the significance level. Alpha by 2 will be 0.025. So 0.025 corresponding to 0.025 value is 1.96. So this is the E value. Considering the sample size of 25, now if we take a sample size of 100, see here the width was 1.96. Now the width has become 0.98. Our width has become reduced, means our precision has increased. Remember the concept of precision. I am telling my x value lie between 2 to 5. Okay, I am telling my x value lies between 2 to 5. Or if I tell my x value lies from 1 to 10, which is more precise, my first statement is more precise. I am telling my x value is lying from 2 to 5. And other, when I am telling my x value lying from 1 to 10, I am a bit imprecise. My precision is going down. Okay, so here when the width decreases, precision increases. And Apple buyer is willing to pay a premium. This question we have solved it. Remember this question we have solved it. but we will see there is a difference in this, the question what we have solved and what we will be doing now. An apple buyer is willing to pay a premium price for a large size apple. There in that question, our size of the apple was, hypothesized size was given. The buyer wants to buy an apple which is greater than some 2.5 diameter, then only the buyer will buy the apple in the premium price. That was the question. Now he doesn't know the size of the apple, he just know that if it is the size is bigger, then he will pay the premium price. So he just wants to know what is the size of the apples. For that, since he has no idea, so he just finds out the confidence interval. Same question, but the hypothesis value is not given. The buyer wants to test if the apples are sufficiently large with a confidence coefficient of 90%. Confidence coefficient of 90%. That means the significance level 10%. So he takes a random sample of 12 apples from the load and measure the diameters. Okay. So results are given below in this table. So from here, what you will find out from this table? So he want to find out the diameter of the apple. So these are the diameter of the apples are given. So basically he will find out x bar, he will find out s square, isn't it? Okay, so here we investigated a similar problem in the last tutorial. You can check it. So that what was the difference? You see the difference in the two questions. Here it was given if they have as claimed an average diameter of more than 2.5 inch, the buyer wants to, then the buyer will be paying a premium price. But now nothing of that sort is given. And earlier the significance level of 5% is given. Now it is given a confidence coefficient of 90%. When the significance level of 5%, then what is the confidence coefficient? Confidence coefficient was 10%. Confidence coefficient is 95%. So here from this region, see, buyer wants to find out if he is not interested in finding out. He is interested in finding out if the size of the apple is greater, if the size of the apples are more, isn't it? So what he will do is that in this case, try to understand very carefully. So he wants to find out if the size of the apple is more, then he will pay the premium price. So in this case, he will definitely not want to find out what is the size of the apples lies in what range. He wants bigger apple, more the bigger, more the better. Okay. So in that case, he will just find out what is the lower confidence interval, because the apple can be how small. From the sample, apple can be how small. So more the bigger, more the better. So he don't want to consider the lower upper confidence interval. He will just find out the lower confidence interval. Okay. And if this question would have been a hypothesis testing, then remember we have here also we have checked for greater than condition. Mu is equals to 2.5, mu greater than 2.5. When mu was greater than 2, alternate hypothesis was greater than 2.5, then our rejection region was in the upper tail. See the difference. Our rejection region was in the upper tail when we want to check it for greater. When we want to check it for greater, our rejection region was in the upper tail. At the same time, for the same, we want to look for greater. But when we find out the confidence interval, for when our interest in finding out the greater, so when we look for the confidence interval will always go for lower confidence interval. Why? Because we want to see how less it can go, how small it can go. Greater means it can be any value. We don't want the interval for that. So t value for 1 degree of freedom, since we are interested in finding out there's a greater, there's a one portion, so we will not consider as t alpha by 2, it will be just t of alpha. T of alpha means t of 10. 0.10, sorry, t of 0.10 for 11 degrees of freedom, t of 0.10 for 11 degrees of freedom. In the table, if you see, you will get this value. In the last problem, in the last tutorial, I have showed the t table. Here we could see this value. So this is my t alpha. Okay. So from the sample, I got, this is my x bar sample. This is my, from the sample, I got x bar value. I got s square value. Okay. So now I just have to find out the lower confidence interval. What is the lower confidence interval? This is my lower confidence interval, x bar minus t alpha. This is x bar, this is x bar, this is t alpha, x bar minus t alpha. Then what is that? S square by n, square root of s square by n. If I would have interested in finding out the upper confidence, then it will be x bar plus. If I am interested in both finding out the lower and upper, then my alpha will be alpha by 2. Isn't it? So since I am interested here in finding out the greater, I don't want the lower regions. So it will be alpha, x bar minus t of alpha root over s square by n. So putting this value, I got this is my value. My lower bound, that my apple can be as small as 2.60. The size of the apple will start from 2.60 to any value that I have not checked. I am not interested because more bigger it's better. So this is my lower value. So this is larger than the required size of 2.5. And if you see, if you remember, if you don't remember, I request you to please go back to the tutorial. There in that, for the same problem, all the data were same. There we have checked for hypothesis mu is equals to 2.5, mu greater than 2.5, and we have rejected the null hypothesis mu equals to 2.5. See here the confidence interval also says so. Mu equals to 2.5, it is definitely, it would have been rejected because my lower bound is only 2.6. So mu is equals to 2.5 will definitely be rejected. So this is the larger than required value of 2.5, again agreeing with the results of the hypothesis test that we have done in the last tutorial. Okay. So again I am coming back to the case study 2, which I have used in my first lecture of statistical inference. And here I am reframing it a bit. How I am reframing it? Here like a medicine production company packages medicine in a tube of 8 ml. In maintaining the control of the volume of medicine in tubes, they use a machine. To monitor this control, a sample of 16 tubes is taken from the production line at random time interval and their contents are measured precisely. Okay, these are the volume of the different volume of the samples what we have taken. Okay, now this was my scenario which was presented. This was my scenario which was presented in my previous lecture. I have used this as case study 2. I have used in many of my discussion this same example. Now I am changing it a bit here. What is my change? I am reframing it. Suppose the volume of the medicine in at least 95% of the tube, 95% of the tube be within 0.2 ml of the mean. Volume should be within 0.2 ml of the mean. Okay, so whatever is the mean volume, it should be within 0.2 ml of the mean. That means if this is the mean, so 0.2 ml means 0.1 is this side, 0.1 is this side, 0.2 ml of the mean. This is 0.1 ml, this is 0.1 ml. This side is 0.1, this side is 0.1. That's what we want to check. Test if the filling process is in control using the given data. This is what we want our variance to be. I mean our standard deviation. It is when it is given 0.1, it is not variance. When it is given within 0.2 ml of the mean, I think you can understand it is not talking about a variance, it is talking about the standard deviation, isn't it? So how much it is changing from the mean? It is changing 0.1. So we need to check whether our volume is within 0.2 ml of the mean. That means maximum we can what we can bear is a standard deviation of 0.1. Okay, that we have to check. So if the standard deviation is 0.1, so what will be the variance? Variance will be 0.1 square, right? So what will be the hypothesis we have to check? Sigma square, that is variance is equals to 0.01. Here again, null alternate hypothesis, we will check sigma square not equals to 0.01 or greater than. I am claiming that we will not check for not equal, we will check for greater than. Why? Because when it is given within 0.1 of the thing, so anything which is less is covered there in the null hypothesis. So what we have to check whether it is greater than 0.01. Within 0.1 means anything it is less than between that will be here only, isn't it? Null hypothesis. So what we have to check whether it is greater than 0.01. So it is again a one-tail hypothesis, that is where sigma square we have to check for 0.01 and our alpha is 0.05. Okay. So what is the statistics for here we'll be using, because we have to infer about the population, we'll be using chi-square distribution. The statistics that is used is n-1 s square by sigma square. From the data that is given, we found this is the s square value, our sample size is 16, we got the chi-square value 47.61. Fine. Now we'll have to first we should have calculated a rejection region. according to hypothesis testing, this rejection region should have been calculated here and before calculating the statistics. Rejection region is first we calculate the rejection region, then we try to find out the statistics. Here anyway, you understand the thing, that is okay. So the rejection region, see now when we are interested in finding that it is greater than 0.01, so where will be our rejection region? It will be in the lower tail or in the upper tail. This is the lower tail, this is the upper tail. This is chi square alpha by 2, this is chi square 1 minus alpha by 2 if it is two tail. If it is single tail, first let me delete this. Since we are interested in here single tail, it is something of this sort. It is not a normal distribution. Chi square is very much a skewed distribution. So we will be interested in the upper tail or lower tail. This is the upper tail, this is the lower tail. So when we are interested in finding out the greater than 0.01, our rejection, our null hypothesis is less or equals to. So if we get a value greater, that means we are rejecting the null hypothesis, isn't it? So it will be, our rejection result will be in the upper tail. So basically we have to find out what is the rejection region taking the significance level of 0.05, because it is one tail, we will not do alpha by 2, but it will be 0.05. What is the chi square value for the alpha? 0.05 with degrees of freedom. How much was the degrees of freedom? 15. For 15 degrees of freedom and alpha is equal to 0.05, we will find out what is the chi square value, that is the rejection region. So if a rejection region value, if this value is greater than the rejection region value, then we reject the null hypothesis. So what is the rejection region? Rejection region is 24.996. Rejection region for 15 degrees of freedom, significance level of 0.5 from the chi square table. If you see the chi square table, this table is available in all standard textbook. Even if you don't consult a standard textbook, you just Google. In the Google, you just write chi square table, Z table, whatever it is, you will get the table. Okay. So this rejection region is for value greater than 24.996. What is our value? Our value is 47.61. So definitely we reject the null hypothesis. Okay. So considering the test statistics, the null hypothesis is rejected. Okay. Now null hypothesis is rejected. That means my sigma square value is greater than 0.01. Fine. Now greater means how greater, how much greater? Let's find that out. How will you find that? We found that our sigma square value is greater than 0.01. Now how much is greater? How much value is sigma square? It is greater, I understood, it is greater than 0.01, but how much is that? So we will find the confidence interval. Okay. So this is how we can find a here again. Here which one confidence interval we will find? It is greater than 0.01. I accepted the hypothesis that it is greater than 0.01. So when I want to find out the confidence interval, so what confidence interval I will find? I will find a lower confidence interval or upper confidence interval. Definitely I will find a lower confidence interval. Greater means it can be any value, but it will start from what value? That I am interested in the lower value. Always remember, when we are testing for an alternate hypothesis which is greater than, then my confidence interval will be always the lower, and the rejection region will be to the right. Rejection region will be to the right, and my confidence interval will be the lower confidence interval. If I am checking for something which is less than, then my rejection region will be towards the left, that means the upper tail, and my confidence interval I'll check for my upper confidence interval. Okay, and if it is not equals to, definitely I will look for both lower and upper, and my rejection region will be both left and right, both the lower tail and the upper tail. So here it is greater, it is greater, so my confidence interval will be the upper one. Greater means my confidence interval will be the lower confidence limit. So this is the formula for lower confidence limit. We have seen n minus 1 s square by chi of alpha by 2. Okay. So here alpha by 2 means we will not consider 0.5 divided by 2. We will consider, because it is a single tail, always alpha by 2 becomes alpha. So it is chi of alpha. We have seen it is 24.996. So this is the value. This is my lower limit. So my variance is at least 0.01. Variance in this tubes is at least 0.01. It can be much more than that, but it is at least 0.01. That means the system really needs some change. So if this variance is 0.01, see, this question has asked for standard deviation. Standard deviation should be within 0.2 ml. Okay. So I'll have to give accordingly, I'll have to find out the answer in standard deviation only. If this is my variance, so what is my standard deviation? Is 0.138. So it should be within 0.2, isn't it? So that means my standard deviation should be 0.1, but I got my standard deviation is 0.138, greater than that. Okay, so you see why the null hypothesis is rejected. My lower interval is only greater than 0.1, that is 0.138. So result of confidence interval agrees with the result of hypothesis testing. Okay, so with this I end this lecture here. These are the references, and thank you guys. Thank you.